Please welcome Frans van Rooyen.
Good morning, everyone. That was probably the best rendition of my name I've heard in a while, so thank you. I want to thank everybody for coming today. It's great to be here. Great to talk to you. As the announcer said there, my name is Frans van Rooyen. I'm infrastructure architect for Adobe. Primarily my focus right now is dealing with the container platform and some of the platform things we're building for our SaaS-based offering. So I work there. Pretty good area to work with, interesting technologies. I'm an architect, but I'm first off a technologist. I absolutely love technology, and I think a lot of you here does too. The thing about technologists is we have a tendency of loving the shiny, right? We go out and we see some new technology and we run and we're like, awesome, we're going to go implement this technology. Often we don't realize what problem we're actually trying to solve or why we're implementing that technology. And so from joining this group, this architecture group, I learned quickly that we need to understand the problem first that the technology is trying to solve before we run out and implement the new technology. I'm sure you guys have heard about many technologies that I'm going to talk about today, which is Docker, Kubernetes, Mesos, and the list goes on and on and on. And a lot of people are wondering, is this hype? Where is it going? Microservices, all of this stuff. Getting into this team, getting into this project, some of those questions crossed my mind too. But I think I've drank the Kool-Aid, and I truly believe this is a revolution. So let's get back to the problem. This isn't based on networking. This isn't based on storage or VMs or anything like that. It's actually the core problem that we're trying to solve and where this technology is going to help us. We have a DRE-eyed engineer or a software engineer coming out of university, and this is how he thinks his life is going to be coming into a company that develops software. He has an idea, and he takes this idea and he goes to his computer and he writes some code, right? We like open source, so we have like some of the libraries that's available there. He uses some of those libraries and he takes his code and he writes his service and he publishes and we start making money, right? And the company's happy, he's happy, life's good, right? So this is not quite how it works. This is how it feels. He has this idea, and then this happens. And he's like, what the hell just happened? How am I ever getting my code out there? All it feels like is I'm fixing stuff for other people's stuff, and this isn't what I thought this was going to be at all. This is actually really hard to get a simple piece of software out to the customer and provide my idea or provide value to that customer. So what is actually the problem? What's going on here? Well, it's actually deploying the application. It's actually a really hard thing to do at scale. If you think about it, applications themselves, when we write them, they have libraries, they have dependencies. And trying to keep those dependencies mapped across environments, testing the machine into production, and making sure that the other team is using the same dependencies, it becomes such a complex process that it almost becomes impossible. It's lucky that we do run code in production in this way that's stable, because it's hard to keep track. The bigger the development team, the harder it is to keep track of these things. So what's the solution? Enter Docker, right? Or any containerized platform for that matter. What does a container do for us? It takes the code and it wraps it up in what it says it does, a container, the code and the dependencies. So now we can take that code, we can take those dependencies, that engineer can sit on his laptop, he can write that code and dependencies into his container and publish it out to a repo. And that repo can then be pushed pretty much into anywhere, but it's always going to be the same environment. Those dependencies is wrapped in the container. So it's always interesting to hear the conversations of containers versus virtual machines, things like that. If you think about it, container solves a completely different problem for us in this aspect. It takes a problem from an engineer and wrapping code in such a way that we can get it out to production, versus a virtual machine is more of aggregating the resources, right? Okay. Something interesting happens, though. We have this transformation process that happens, much like any new technology. We get the ops guys saying, wait a minute, something happened. No longer do I care what the role of the machine underneath is, because I get this container, I can run it, and all I need to give the engineer is a very generic machine with Docker on it, or an orchestrator. And that's all he cares about. If I can just give him that machine, then he can get his code out and it'll run. and then I can load some other containers from there, and I can get some performance boosts and all of this other stuff. And if I give them an orchestrator, a piece that runs all the machines together, anyone in here doing VMware, very much familiar with clusters, right? If I give them that cluster or that orchestrator, now that orchestrator can decide where that container runs, right? So we go from this transformation of bits versus cattle, and I think everybody here has heard that analogy, which is actually a really good one. Because we now have a herd of cattle from operations side that we have to manage. No longer the individual roles of the machine. I don't care about a DB server or an app server or any other type of role, cache, or all of these other roles that I have to specifically come in and modify and tune that machine to work for that role. It can be very generic. It can just be part of the herd. If the thing gets sick, you shoot it in the head, it dies, and you put in a new machine, and you're ready to roll, right? Don't really care about other than having that orchestrator platform on there. So for ops, this is a pretty radical transformation. Because of that, now you have what's called a service transformation. The engineer is thinking, wait a minute, I always built my service in a single monolithic type of app. I tried to write everything in there because I was worried that I need to make sure all of the dependencies and all of this stuff is being mapped. I don't have to do that anymore, so now I can just write microservices. Much like anyone being in computer science, right? This is dating me a little bit here. My first computer science class was in Pascal, and the first program I ever wrote was this big monolithic thing, right? And soon enough, you're like, wait a minute, but I'm doing this stuff over and over again, and the teacher comes up and they're like, yeah, you can actually abstract it out. You can do something cool called a procedure or a method, I think in today's methodology, right? But you can abstract these pieces out. That's what microservices are. We're starting to abstract out and saying, let's break this up. Let's make this smaller. You're only doing one single function. You're going to wrap that in a container. You're going to go launch it out into your fleet, and it's going to run in there. And you can independently scale that container or that service depending on its requirements. Scaling a monolith is a hard thing to do. Scaling a microservice is much easier or much more integrated. You can look at the microservice itself. You can decide on where the services need to scale and which pieces don't. Okay, so let's go through to put all of that together. Let's look at the life of a container from dev to prod. We have our DRE-eyed software engineer, right? He writes some code, okay? He pushes that to Git, right? In that repo, he opens some kind of PR or something like that. It sets off that this needs to be a build. He's going to go through some automated deployment process using Jenkins or some deployment tool. That tool is going to go ahead and create an artifact. That artifact is going to be a container. That container is going to be stored in a container registry. That's where we store them. It's going to go up to some kind of orchestrator, DCOS, Kubernetes, Docker Swarm. It doesn't really matter. It is the piece that contains the herd, right, that manages that herd for you. Now that container runs out there somewhere, and happy customer, right? We've made our money. You look at this thing, and this is actually pretty cool. How many Jira tickets did I open to get that piece of software from the engineer to the customer? None. How many ops teams did I get to actually stand it up? And how many processes did I have to go through to get that? None. Now you're thinking, holy crap, that's pretty scary, because you have an engineer being able to push prod code. Yes, it is, but that's where automation is there. That's why pieces like the build systems, things like that comes into play. You can automate this. You can actually get code from the engineer all the way in production in this process. We know because we've done it. We also have seen others do it. This is a successful pattern. If you look at Netflix, you look at Amazon, we heard Netflix speak yesterday, this is kind of like what their microservices footprint looks like. This works, right? Okay. Now, why are we here? You guys are networking guys. You want to hear about containers and networking and what solutions there are. So let's talk about container networking. My favorite quote on container networking, and I think probably the container team's favorite quote on container networking, is this one from Kelsey Hightower. There's no such thing as container networking. There's containers, there's networking, and networking can help solve some of the issues around containers, but there's no product, there's no box you're going to buy that's going to give you container networking. So if your vendor comes to you and they're like, hey, we have this great new solution, it's going to give you container networking, be like, no, there's no container networking. I just need to solve it, right? Okay, so let's go through some essentials here quickly. You have a single node, a host, right? So container runs on it. What happens when Docker actually starts up? You have 3 networks it's going to create. None. So what this actually means is Docker actually does not connect to any kind of interface. Reason why is this is for testing purposes. You have the host, not very ideal situation here, and we'll talk about that in a second. What happens here is the container interface connects right to the host's interface. Thomas did a great job here of actually explaining something very important about containerization and microservices. They love port 80 and 443. That's their interface. That's how you get to them. What happens when I spin up 2 services on the same host that uses the same IP and the same port? I kind of feel silly asking this group that because you guys know very well what happens when that happens. It just doesn't work, right? So we need to get some way around that. So the default networking option on a Docker host, single host, is called bridge, right? So it spins up a bridge network, and this is how it looks, right? So it just spins up a bridge. It pushes all the containers to that bridge, adds some IP tables, and then out you go. Okay? However, now you're going to think like, holy crap, those containers can talk to each other, and what if they're supposed to be secured and segmented and all this other stuff? Sure. You can actually spin up multiple bridges on a host. You can share containers among bridges. You can isolate containers from bridges. You can do all this stuff that makes the container secure on that host. The problem is it defeats the purpose. We're not just talking about one host. We're talking about hundreds, thousands, and most likely tens of thousands of hosts that runs these guys, right? So try to go and set up this configuration and try to keep track on it on every host when you have 10,000, 20,000, 100,000 hosts. It ain't pretty, right? You guys complain about the switches you have to do. Try and do this. It just doesn't make any sense. So we need something else. Okay, well, there's another technology out here with overlays that we can do, right? We can go ahead and say, okay, from my Docker OVS switch, let's create a VXLAN tunnel between the machines, and then actually do an overlay there and have them talk there and use SDN technologies, so forth. Sure, it works. It's complex, though, and we've seen some performance issues around that, too. And as my friend Boromir always say, you don't go just deploy SDN just because you want to. Okay? So not a great solution, especially in this world. So then we have something that was called underlay technology for containers. I saw somebody else talk about Calico yesterday. It's a great project. It's actually the idea here is to provide layer 3, so big, fat layer 3 pipes down to the host or the containers. So that's all you get. Very simple, very clean. You don't get fancy stuff here. You just get layer 3 down to the host. But it cleans up quite a bit for you. Now you're asking, where am I going to do my policy enforcement? Where am I doing my load balancing? Things like that, right? This is where Thomas mentioned quickly on service mesh, right? So if we look at some of the stuff that's coming, some of the things that's actually taking care of our problems here in the container world, service mesh or some of the things that Istio is doing actually provides us something more than what we had before, which is this layer 7 versus layer 4 implementation. Istio itself takes a load balancer, and if you think about containerization, you have one container running that service, but most probably not. When you build that service, you want to scale it, so it's going to be one or many, and most probably many, running that service that needs to sit behind a load balancer, right? That is then going to be put out to the world, and many other services that has that same structure, load balancer services in the back, wants to talk to each other. So you have this service mesh thing going on. You want to secure it. You want to make sure you do traffic management. You do the fault injection, rate limiting between them. All of these pieces needs to be built out. So a core piece of what Istio actually is what's called the Envoy proxy, right? Envoy is Lyft's proxy version, and then Istio took that and modified it for containerization, and it's one of the pieces that is core to this piece. And like Thomas was talking about here, is the sidecar to it. It has something called Istio Manager, and it goes out and does automatic scaling. One of the big things around microservices is that you want your proxy layer to be very dynamic, being able to scale. Istio enables you to do that. But what about performance? When you do everything in layer 7, what are you going to do? What are you doing about performance? And this is where BPF comes in and some of the work that Cilium has done. This is great because now we are able to abstract to layer 7, but we're also able to get kernel-level performance, right, on a very, very large scaling layer of containers. So a little look in the future here. If we look, the guys at AT&T actually has done something pretty cool. It's called Torque, top-of-rack controller. And what they did is they took a Linux-based switch, right, running SnapRoute, and all of these other pieces, and they actually introduced that switch to their orchestration layer. So what that means is that switch isn't just a switch anymore, but it's actually a node in their orchestration layer. So it's actually a Mesos node. It could be a Kubernetes node. In this case, they used Mesos. So the switch now can run containers. We actually did this to do initial deployment. When a switch can run to containers, you can actually use, from an engineer, from a networking engineering perspective, the same methodology that we use to build our own code. You can start doing functions. You can start doing pieces that you need on your switch through a very prescriptive build process. You can submit it to Git. You can build it through Jenkins. It can fit into a Docker container. That Docker container can launch. And now your orchestrator can become opinionated. It might decide to launch your container on a server because that's the layer that the performance are required. Or you might have some kind of RTB app that you want to have edge capability, and then the Docker container runs on the switch. The switch now becomes something that is yet another compute device. The thing about microservices, the thing about 12-factor, is that it treats all infrastructure as abstracted layer. There is no such thing as storage arrays, or really switches, or servers. It's all just abstracted compute that we can use any way we want to prescribe to it based on what that role can do. Switches is an edge device that can provide us quick access from one service to another. A server might be something that provides us statefulness or stateless apps or more performance in the CPU. The good thing here is that now we're fully abstracted, and moving into the cloud or into the data center doesn't really matter. The platform that we get is a very generic one, which Mesos, Kubernetes, these pieces give to us. So the interesting thing is, from a software perspective, what we're wanting to do and what we're hoping the engineers are starting to realize is that the problem that we're trying to solve, or the revolution that the engineer went through to be able to get to deploy code very fast, is the same one we should be going through as infrastructure specialists. We should be checking our stuff into Git. We should be forming build processes to actually stand up our infrastructure. We should be using pieces like SnapRoute, Terraform, things like this to actually describe and build programmatic way of building infrastructure. And that's it. Thank you very much.